Hi students, I hope you are listening and enjoying online lectures. In this lecture we will study scintillation detectors. A scintillation means flash of light. There are certain materials which produce scintillations. These materials are called scintillators. These scintillators have great importance in detecting various radiations. Detectors which use scintillators are called scintillator detectors. Now we will study the principle of scintillation detectors. When an ionizing radiation passes through a scintillator, it excites the electrons in the atoms of the scintillator. These electrons quickly fall back to their ground levels, producing scintillations, that is visible photons. The visible photons are sent to photomultiplier tube. The visible light photons are converted into an electrical signal in the photomultiplier tube. This signal is used to measure the intensity and energy of the incident particle. There are various materials which can be used as scintillators. Let me introduce some common scintillators. One is inorganic scintillator. Examples are thallium activated sodium iodide and thallium activated cesium iodide. Second category is organic scintillators. Examples are anthracene and stilbene. There are also gaseous scintillators which works on noble gases, in fact the mixtures of noble gases. And fourth class is glass scintillators. Well, the principle and working of these scintillation detectors is almost same. So here I will discuss only one such detector which is very common and important detector, that is thallium activated sodium iodide. Here you can see the construction of the sodium iodide thallium activated detector. The scintillation crystal, that is sodium iodide, is put in an aluminum casing and is attached to a photomultiplier tube. There is a window which allows the radiation to enter the detector. It is usually made of aluminum or beryllium. The photomultiplier tube consists of a thin photocathode and a series of diodes. Now let us see how scintillation process takes place. The scintillation process of inorganic scintillator can be understood in terms of the allowed and forbidden energy bands of the crystal. The lower energy level band completely filled with electrons, as you know, is called the valence band. The higher empty band is called the conduction band. The two bands are separated by an energy gap called the forbidden band. When ionizing radiation loses its energy in the scintillator, electrons move from the valence band to the conduction band. The electrons are free to move anywhere in the crystal once they are in the conduction band. These electrons leave behind holes in the valence band which can also move. The gap between valence and conduction band is of 8 electron volt. Due to the de-excitation of electrons directly from the conduction band to the valence uh, band, visible photons are produced. The energy of the emitted light is equivalent to the band gap energy of sodium iodide crystal. Therefore, the scintillator can be opaque to its own light emission. Therefore, the scintillator material absorbs the emitted photons. This problem can be solved with the use of thallium activator. Thallium is added to sodium iodide in small amounts, that is about 1 atom per 1000 atoms of sodium iodide as an impurity. The thallium impurities are also called activators. That's why the name thallium activated sodium iodide detector. Thallium atoms produce extra energy levels within the forbidden band of sodium iodide. When the hole comes into contact with an activator site, it acquires an electron from the activator. This now produces a hole in the activator site, into which an electron from the conduction band can drop. Within the activator site, the electron can de-excite from an excited state to the ground state and emit a visible or near visible photon. The energy of this photon is less than the band gap energy of sodium iodide. Therefore, the sodium iodide crystal becomes transparent to this photon. Now let us discuss the working of scintillator detector. Scintillator detector is mostly used to detect gamma rays. When an energetic gamma ray enters in the sodium iodide crystal, it interacts with the atomic electrons mainly through the process of photoelectric effect, Compton scattering, and pair production, as we have already discussed. Consequently, a fraction of gamma ray energy is converted into the production of light photons of much lower energy, as I have already explained. The light flashes produced with the gamma ray absorption enter the photomultiplier tube, where they liberate electrons from the photocathode through the photoelectric effect. These photoelectrons are accelerated towards the first diode, which is kept at high positive electric potential. Gaining high kinetic energy, each photoelectric electron that strikes on the surface of the first diode produces many more electrons. Since each succeeding diode is at higher potential, these electrons keep on multiplying due to the same process. For example, if one electron bombards the first cathode, approximately 10 electrons are produced from that diode, and those 10 electrons are then directed towards second diode, and these 10 electrons further produce 100 electrons, and so on. At the end of the last diode, a measurable amount of electronic charge is produced in the form of an electric pulse, which is further processed through amplifiers. The pulse height of the output signal is directly proportional to the energy of the incident gamma ray. Thus, number of such pulses measures the intensity of gamma rays, and the height of the pulse measures the energy of the gamma ray. There is a very important um, quantity in detectors which is called resolution. The energy resolution of a scintillation detector is its ability to resolve peaks whose energies are close together. Suppose this is the pulse produced by the detector. Full width half maximum is width of the peak at the half of the pulse height. Then the resolution in percentage is defined as full width at half maximum divided by energy at the peak into 100.